Bonsoir, Toulouse. Recently, there was a space impact. A giant meteorite hit the surface of the Earth and produced thousands of fragments in a giant explosion. Unfortunately, one of those fragments directly hit my kneecap. Very unpleasant. This limping, this pain. I can tell you, after such an experience, you really get lost in thoughts. Where do these meteorites come from? Where do we all come from? Where do we go? Well, astronomers search for answers to such questions in the universe. For that, they use giant telescopes, like the ELT, which is currently constructed by the European Southern Observatory in the Atacama Desert in Chile. Such telescopes are used for observing astronomical objects, like, for example, this galaxy. From such a galaxy, light comes down to Earth in form of light waves, shown here as the green lines. Please imagine those as continuously traveling downwards, just like waves on the surface of water. In the telescope, these waves are gathered, focused, and produce a sharp image of this galaxy. The problem is, if you just let this process happen, the image will look like this: unsharp, contrast reduced, blurred. Why is that so? Well, if you have a meteorite fragment in your kneecap, you have time. You sit around in the garden, watch the cars driving by, musing about the usual questions: where do all the cars come from, where do they go, etc., etc. And suddenly you realize that above the road everything looks flickering, like a Fata Morgana. This is caused by the hot asphalt. It causes turbulence in the air, and this distorts the propagation of the light waves. And here the same thing happens. Compared to the universe, our planet is actually very hot. It causes permanent turbulence and temperature fluctuations in the atmosphere. So let's, for example, assume that in this position the air is a little bit colder than in the surrounding. Then it is more dense, and light, as it travels through, gets slowed down a little bit. It lags behind, and we get dents in the light waves. If air is a little bit warmer in here, the opposite effect happens. Light goes faster through it, and we get dents in the other direction. The resulting wavefront that enters the telescope somehow is deformed, and this causes a mess in the focusing process, and this causes the blurring of the image. Now the question is, of course, what can we do against it? Well, first, there was my appointment at the medical doctor because of my knee. I had to put off my shoes. He looked at my leg and he said, "We have to do computer tomography." So I was brought to the CT scanner. My leg was pushed inside a tube and X-rayed from several directions. From these images, in several perspectives, a sophisticated computer algorithm calculated a three-dimensional model of my kneecap, exactly showing the position of the meteorite fragment. Based on this, the doctor could develop a therapy specifically adapted to the individual needs of the patient. And he said to me, "You need rest, stay in bed." And here we can do the same. I'm not talking about staying in bed, but I'm talking about tomography. We can measure such wavefronts, the shape of such wavefronts, if light stems from a point source of light. For example, from a star. Stars are perfect point sources of light. If we now consider the light from the left star, the according wavefronts are inclined a little bit to the left. As they travel down through the turbulence, they get their dents and enter the telescope in a specific shape. And this shape can be measured. Light from several stars performs a wild and crazy dance through the turbulence in different directions all at the same time. And we can measure all these wavefronts. Based on this information, a sophisticated algorithm, similar to that one running in the CT scanner, can actually calculate the three-dimensional structure of the turbulence. That is tomography. That's what we are working on at our institute. That's why I just tried to dance the word tomography, such that this keeps in your mind. However, if we know this three-dimensional structure, we can directly calculate the shape of this wavefront. Now, deformable mirrors come into the game. These are mirrors made of an elastic material. Placed in the correct position, they can be adapted to the shape of the wavefronts. The point is that the reflected light is a plane wave again. By that, we get a sharp image again. Such a system is called adaptive optics system. And it shows the really cool thing about math. With the same idea and accordingly similar algorithm, you can solve completely different problems, like for instance in the CT scanner and in the telescope. That's the power of abstraction. From future telescopes, we expect an image quality so high that it will be possible to take direct images of exoplanets. By spectral analysis of this light, we can draw conclusions on the chemical composition of the atmospheres. If we would find substances that can only evolve in biological processes, then we would have a direct proof for the existence of extraterrestrial life. This would enable us to find answers to essential questions. First of all, who threw that meteorite upon my knee? And what else can we learn about the aliens? What is the state of their development? Do they have some kind of culture or civilization? Maybe even ahead of ours. Maybe they're even ahead of stereotypical gender roles. Who knows? What is their attitude towards us? Are they peaceful and friendly? Are they willing to share their knowledge with us? Or do they just want to steal our knowledge? Maybe our technology? We don't know. Now. But we will know if we get sufficiently sharp images from the universe. In this sense, if you ever want to construct a giant telescope, just call us, the Industrial Mathematics Institute of the Johannes Kepler University in Linz. In this sense, I thank you for your attention and wish you a pleasant continuation of this evening.